Thanks. And I'll also be giving a demo at the end, so something you can try out for yourselves. Very quickly about me, I'm a student at the University of Toronto, and I'm working on the Finch mission. The emoji is apt because that's a literal satellite we are launching with SpaceX. And I'm also a member of the Kubernetes organization and a part of the 1.26 release team. And I, of course, love open source like most of you all here. So I want to start out with the motivation for this talk by saying that most machine learning models don't get deployed, which is kind of the hard truth. And if you put numbers into the place, 90% of machine learning models don't get deployed, which is a big number. A lot of it is just due to is just due to the iterative nature of machine learning. You work on a lot of models and probably some of them turn out right, or just a lot of iteration, experimentation in the initial phases. But a lot of it is due to improper data management or not proper serving techniques for your machine learning models. So that's what I want to talk about today. So in like the next 30 minutes, I want to talk a bit more about deploying models and some of the things that could be considered as problems and how could you get around them when you're deploying models on Kubernetes. So this is a very common misconception, and since we are at Data Management Day, I think a lot of you might have already known about this, but I'll go through it. So it is a very common misconception that modeling code plays a big role. Well, it plays a big role, but some of the other parts of the entire system, like the serving infrastructure, for example, are pretty big. Modeling is just like a little part of it. So you do need to put in just as much time for serving infrastructure, configuration, data collection, all of these other processes, not just your modeling code. And if you would, statistically speaking, if you would want to put in numbers, it would consider like 5 to 10% of your whole pipeline, just the modeling code. And I mean, that differs according to the nature of your pipeline, but statistically speaking, it plays a little role. So now I want to talk about why should you care about machine learning deployments and not just think about it as ops problem now that you have made a model or made some system. I want to start by talking about why you should care about machine learning models by saying that it's not just the same format. You wouldn't ideally want to deploy a Jupyter notebook, though you can. Most of the times you'll be probably creating your models in Kubeflow notebooks or something similar, and you'd ideally not want to deploy that. And so what all things should you take care of while deploying a model, and what do you need to actually deploy a model? So first off, I want to package the machine learning model. As I was saying, it should be optimized enough to make an inference. It should not be optimized enough to do the training, to do the experimentation. It should be optimized enough to make the inference. And there is a big difference between both of these. So first off, I want to package the model to allow it to make inferences efficiently. Next up, I want to host the model on a server, which is very explanatory. And then comes the part of the server, which contains a lot of things: auto scale, global availability, making sure your model has lower latency. And all of these look familiar because a lot of these problems, auto scaling, for example, are natural to you while using Kubernetes. So a lot of the server problems, so to say, are already handled pretty well by Kubernetes. But some of the other parts which are specific to machine learning deployments are not so well handled. For one, creating a machine learning API out of this could be considered a pretty involved task. You need to, while creating an API for your machine learning model or your system, you also need to think about model versioning. you would rapidly iterate, you would have multiple models, not usually the case with standard systems. You also need to think about batch predictions, uh, which is again not something you'd want to do in a standard system, but batch prediction is a great way to conserve your hardware. And the simple idea is that you take in multiple requests and then process them together, which kind of gives the idea of a batch. So you take in a batch of requests, process them together, and this is particularly useful if you are using something other than a CPU, probably a GPU or a TPU, and those are costly. So batch prediction becomes a great idea over here, and something that is very commonly needed and supported for machine learning models. Okay, so now we know what is needed for deployments, and I want to talk about simple deployments and why this and why we are not talking about simple deployments going forward. That now that we know what all consists of a successful deployment. So I want to start by showing an example of Flask. If you have been deploying machine learning models earlier, a lot of blogs, a lot of videos, pretty much all of them say that Flask on Kubernetes, Flask on serverless platforms, wherever you want it, essentially, is the right way to deploy machine learning systems. And this is just a sample code. A lot of this is undefined, like what's a preprocess function, but just a sample code. You have all of that written down. So this is how a simple Flask app would look like. And I want to start by saying that there is no consistent APIs over here. Here I have a route called /classify. I can create a route called /classify2, /classify my name, anything I want. So there is no consistent API over here. The model versioning support is also not that apt. You'd essentially need to manually do all of this. It's simply put not optimized for machine learning type of deployments, though it might be pretty nice for standard deployments. There is also no mini batching. I mean, you can implement it yourself and probably spend a year, but I've never tried mini batching with Flask, though it might be possible in some cases. And this is also inefficient for larger models. If you have models which are pretty large, GBs large, then this becomes a pretty inefficient way to deploy your model. And this code might look familiar. It's a simple Flask code, or if you might deploy it some other way. But I just wanted to sort out the problems you face with these kind of simple deployments, which are not so much geared towards machine learning. So I want to talk about TensorFlow serving. TensorFlow serving is a project I've been using for quite some while. I've also been contributing to TensorFlow for quite some while. So I want to motivate by talking about TensorFlow serving. So TensorFlow serving is a project that builds on top of and thinks about all of these problems that we talked about, and allows you to deploy your models easily. So this is actually a part of the TensorFlow extended ecosystem, which contains multiple tools. TensorFlow serving is one of the most popular tools from the TensorFlow extended ecosystem, and which is what also we'll be taking a greater look at today, and fits right into the context we talked about. So I first want to talk about exporting the model, which is the first step of our successful deployment, if you remember the slides from 5-10 minutes ago. So one of the ways to package your deployment would be the saved model format, which is pretty popular. And all this does is has your graph definitions as protocol buffer formats, and then you have the saved model directory with the auxiliary files in the assets folder. You have variables, which are essentially the weights for your models, and then of course is the graph definitions as a protocol buffer. So with that, you have now packaged your model in a way that it's efficient for inferencing from the model, and now you're ready with this. And now you're ready with this saved model. Your model, all your modeling code which you wrote, is now as a saved model. Now you actually want to deploy this. But this is a great step to do because now it's already in a pretty optimized format for inference. So with that, I start using TensorFlow serving now, and I simply call the TensorFlow model server. This is a basic example, and we'll build on top of this. So we'll start off with a very simple example where I make a REST API out of it and host it. Um, I so then I make a REST API out of it, run it on port 8501, have a model name and have them name as test because I couldn't think of better ones, and then I specify the saved model directory which we created in one of the previous slides. That is a very simple way of using TensorFlow serving, and you could also have support for not mounting the file system altogether. So have something like have the models from something like Google Cloud Storage or even S3 or wherever you want it. And we'll talk more about some of the features this allows us to get, especially polling and model versioning. But right now I want to talk about the inference. So with the very, very simple code example, I wouldn't even call it code, just a few lines. You have created a gRPC API, you have created a REST API for your model, and these are consistent APIs. How are they consistent? We'll see. So this is how you would inference from it. A template to inference from. The test is what my model name is. And the APIs are pretty consistent. I couldn't have an API with some random /path. You can also get inference from particular model versions. And this is a very simple example. We don't think much of this. We'll show this in a demo later, in some while. But I also want to talk about, so the previous slide is actually an example of making a REST request to our deployment, and which is pretty well known. You can easily make a REST request from your model, from the deployment you made. And I also want to talk a bit about making gRPC deployments. Some of you might know gRPC. If you don't, gRPC is a CNCF project, and it's pretty useful in such a use case. It allows you to have better connections for your API. All of your data is converted as a protocol buffer format, which means that there are designated data types for what the model is expecting. It's also more efficient than REST, at least for this use case. And contrary to the REST to a REST API, it uses gRPC stubs to send and receive data. So creating the gRPC API is pretty beneficial for our use case as well, and that's also something you could do, as I showed earlier in your earlier deployment. We also have the model meta API, which allows you to simply track the telemetry information for a model all within the same API. And I'll not talk a lot about model metadata right now since I'm running out of time and also have a demo. But lastly, I want to talk a bit more about batch inference, because this was one of the things we said we wanted in our system, and we haven't really talked about it. So batch inference allows you to use your hardware efficiently, and it's also pretty useful for saving costs and compute resources. Essentially, what you do is take in multiple requests, store them, and then run your model on a batch of inputs instead of running it on each input, because the loading for the model is pretty costly here. So running it on batch of inputs makes a lot of sense. And this is also really cool for larger models, where loading is a very, very computational. Loading the model is a very computational task. A lot of you might have worked with containers in the past, and one of the big things. I'm going a bit off track, but one of the big things that WASM containers pose over Linux containers is the fast startup time, and which is pretty analogous to what we are talking about right now. We don't want to have a lot. So model loading is a very computational task. and this happens after the container is started. So which is why batch inference can be really helpful for this use case. And you can easily have a batching parameters file where you specify where you can specify and customize how the batch inference happens, and you can add this to the deployment in the same way as we showed earlier. We showed a very simple example of the deployment earlier. This is how you can modify it to do what we wanted. You can specify things. You can specify things like how often should it batch, how many requests should it batch, and so on. You would simply load this configuration file when you start up, and allow your deployment to use batch inference. So before I go forward, actually, I also wanted to talk about some of the customizations possible here. These are just some of them, and I specifically included some customizations for model versioning as well. So especially if you see the polling related arguments over here, you also have the ability to poll models. So one of the things we saw earlier was you do not need to mount a file system. You can directly get your model from Google Cloud Storage or something. And so the poll is essentially reading the bucket multiple times to see if a new model version has been found. If a new model version has been found, make a new deployment with the new model version and still serve both of your versions. So this is what polling essentially means, to look back at the storage bucket again and again to allow you to properly version your models. And you can also customize that or have support for that in the same way I showed earlier. Update the configurations. So with that, I come to the end of slides. No, it's not. Thank you. I'll show a demo. So I'll also need my laptop here. So I'll just get that, and I'll show a live demo of what we talked about. Okay, so now we'll see a live demo of TensorFlow Extended deployed on Kubernetes in action, and so I'll just set some context for what is happening here by going to CVO, and I'll just do. I just have a Kubernetes cluster already created for me. I'm just using CVO for my own self. You can literally use this on any other cloud, of course. So I have a cluster called cndm-day, and my kubectl here is configured to use cndm-day. The code space is still starting up, but the way this has worked is I already have a bare bones cluster over here, and I'll show you some of the things I've deployed over here. So especially I want to show the deployments.yaml, which uses a TensorFlow serving image, and shows it what path I want, and shows it where is my saved model, and it also allows me to create a this should be better, and it also allows me to create REST APIs and gRPC APIs, which I'm actually doing over here. I'm also taking the model from a cloud storage bucket, and I'll be polling that model. This is a simple ResNet model. Of course, feel free to, you can use this in the same way with other kinds of models. I have a load balancer for my HTTP and my gRPC APIs. So with that, by the way, all of this is open source. You can try this out just the way I have done it. Okay. So I have deployed all of this on my Kubernetes cluster. I have some commands over here for you if you want to follow them in the exact same way I did. Yes, I spent some time writing docs, though it is just a demo. But with that, we'll actually try to make a prediction. And what I'll do is I'll first get the external API for my service. So let's actually go over here and do kubectl get svc. So once I've done that, I know that my image classifier load balancer has this external IP, to which we'll say that we want to make a request. So we enter the same, and I mean this is a simple demo, uh, just made to try it out. You would probably do a lot more than this, not put in the external IPs and all of that. But this is just a demo to try it out. So I also have locust if anyone wants to try out if anyone wants to try out auto scaling, which is pretty useful. But right now I'll not be showing auto scaling. I also have a locust response for that. I also have a locust.py Python file for that, but I'll not do that right now. I have a request body, and what the request body is essentially is an encoding of an image. The image is of Grace Hopper in a military uniform, which is just an image I found on the internet. It's encoded as base 64, and that's what my request consists of. This is a ResNet model, and if you remember, if I go back to the config map, I deployed a ResNet model over here. This is my ResNet model, which is stored in a Google Cloud Storage bucket. Of course, you can use anything else, but the ResNet model is created to identify all kinds of images. It was trained on ImageNet, which has 1001 labels, and then there's a variant of 21,000 labels. We are actually on the 1001 label variant. So it is trained to identify 1001 different kinds of images. So we'll actually give this a try. And oh, yes, I'm not in the right directory. So I'll just go to this demo, and then I'll run this. And there I actually get it. This was actually, so as I was saying earlier, this was an image of Grace Hopper in a military uniform, which is a pretty popular image on the internet. I can also, actually this one itself, yes. So this was the image I put in, encoded as base 64, and this is what the model told me. And instead of like seeing the outputs of the model, what I want to show you is TensorFlow extended deployed on Kubernetes, solving all of the things we talked about. So with that, I come to the end of my talk, and thank you so much for hearing to me.